Hello, and welcome to the Jacobi Palletizer tutorial. My name is Swapnil, and I'll be walking you through the setup of our Palletizer software. In this video, part 2, we will be exploring how to translate the robot cell we saw in the previous video of our Palletizer tutorial series into our digital online tool for computer-aided design and engineering of robotic cells, Jacobi Studio. So, once you log into our website, studio.jacobirobotics.com, with your Jacobi account, you should have access to this platform where you can access a list of all your past projects or make a new one. Here we don't have any old ones, so let's just make a new one and it'll send us here. This is the 3D environment within which we can model the features of our cell. Let's start by modeling our pedestal upon which our robot is installed. For this, we can actually use a combination of measurements from the real cell as well as the ability to insert base geometries. We can create basic shapes like cubes, cylinders, and spheres. Here, our robot is installed on what can be represented by a cube base and a cylinder on top of it. So let's do that. However, some obstacles can't be represented so easily. What about our conveyor, for example? Well, in that case, we can upload a pre-existing 3D model of that conveyor or any other obstacle to our cell. We do it like this. If you already have developed your cell design on another software like SolidWorks, we make it easy for you to just drag and drop your designs here so they can work within our Jacobi framework. All you need to do is simply have or export your designs in one of our many supported file extensions like .step, .glb, among others, and you should be set. What about the robot? Well, for the robot itself isn't an obstacle, so we don't want to upload a file of that. Instead, what we do is go to the menu and select Add Robot. So here, you can see the wide variety of robot brands and types that we support. In our case, we pick this. When we insert a robot this way, it ends up at the origin of our project. So clearly this doesn't match up with reality just yet. But we can change that in the robot settings. Here you can go to the base tab and actually translate the robot like any other obstacle so you can set it in place where it should be. Now that we have our robot in place, we can inspect and see how we can control the robot and move it around. At any point, we can use this tab here to set either the joints of the robot and inspect how it looks in real life, or set the desired Cartesian value at the endpoint and see which robot positions could yield that. You can even jump to defined waypoints here, but we'll get into that later in this video. In any case, you can use this to test robot cells you're working with to confirm that your robot can in fact reach everywhere within your cell. This is very important for palletizing, and we as Jacobi want to enable you to be able to test and confirm as much as possible confidently within the realm of simulation before you get along to real deployment. Of course, our robot isn't complete yet. Our robot has a gripper in real life, but not here. So let's change that. Let's go to the End Effector tab. Here, I can add an obstacle to the end of the robot to model that gripper. I have a 3D model right here. But as before, you can quickly model anything here with a basic geometry to represent it in the abstract. But we have the real deal right here. Once it loads, we see we have the gripper installed on the robot. Of course, its location isn't quite right, and you can see how the coordinates of the robot don't quite match up to where the gripper is yet. But don't worry, we can fix that. First, we can access this obstacle and translate it till its position actually makes sense with respect to the robot. Once that's done, we can just move around the TCP of the robot endpoint. This is called the flange to TCP, and it's a transformation between the coordinate frame at the end of the robot's flange and the one we want at the gripper pickup point. These are the values I use for this cell. With this, we can also take a look at the last tab we have to control the robot. We have this here for use with our Jacobi motion planning. In the ideal world, we don't need the robot running at full steam always. This is a detriment to the robot's health and long-term operation. So we can define limits for the robot's velocity, acceleration, and jerk here at each joint. We can also limit the positions each joint can reach. By this, we don't mean the limits that the robot joint physically already has. For example, I can't rotate this more than 180 degrees back in either direction, and I don't need to explicitly specify it. It shows up. But what if I have a safety configuration that doesn't like it? If joint 3 brings these two links of the robot too close, then I can set a joint limit and prevent it from ever being considered in planning in the first place. We can make similar calls for velocity, acceleration, jerk, and influence the smoothness of robot operation with as much control as you'd like. In any case, when you first create a robot, these values are auto-populated with the robot's designed limits based on its physical specs, so you don't need to specify more if you don't want to. Now that our robot is set up and done, it's important to confirm that the cell is correct. Visually, nothing looks wrong with the way we've set our cell so far, but this is the visual representation. This is only what we see. We need to also confirm that what the robot sees makes sense. We can do that by switching to the Collisions tab. Here, you can see the collision models the robot uses to understand its environment. As you can see, for stuff like cubes and cylinders, the collisions make immediate sense. But for our 3D uploaded obstacles, the collision boxes seem generous. This is deliberate. Not all 3D uploaded obstacles need a high level of detail to capture the collisions. For example, our gripper here, while not quite reflective of reality, is still satisfactory to perform palletizing with. But if we need, for any obstacle, a more accurate reflection with respect to reality, we can achieve that. Instead of auto-generating a collision hitbox, we can manually make it more detailed and reflective of the shape's inherent geometries. It takes a few minutes at most for these higher detail versions, but with this setting, we can accomplish these as well. With this knowledge, let's model the rest of the cell. It is very important that your pallets are modeled as box obstacles. You also need to tag them as pallets so that they can be identified by our software. To do that, all you have to do is this, and press Enter. Bam! Now this box is a special box that Jacobi Palletizer will recognize as a pallet. If you need the visuals to reflect reality, we can do this as well. For example, here's a model of a pallet I have that I'd like to use in my cell instead of this box. What I can do is this. I can place the pallet here, and I can disable its collisions as follows. I can then look at the box here and hide it visually. Just like that, by manipulating these options, I can in the visual scene see a pretty pallet that looks like the one I have. But in collision, I have the box with the tag that is actually going to behave as my pallet. By enabling and disabling collisions and visual this way, you have a lot of flexibility in how you want to render your cell and how you want to model collisions. For example, you might also want to use hidden boxes in the visual to influence behavior. What if I wanted to not let the robot hit the ceiling? Not that it could reach or it'd go there anyways, but I'd want to limit that kind of skyward pointing behavior. What I could do is this. Let's make a box, put it in the sky. Let's say make it this big, and then hide it visually. Now, it'll exist in collision space as something the robot sees and treats as an obstacle, so it won't ever even think of trying to get up there. But we can't see it in our pretty visual of the cell. Now that our cell is done, let's model some points of interest. For example, we want to find a home waypoint, a point where the robot can safely be stopped when palletizing is wrapped up. Let's say we want to pick here. Once we're happy with the location, we can create a waypoint, and it makes a new point right where the robot is last stopped when you click it. You get the option to save it as either a Cartesian or a joint space waypoint. For home, I usually just use a joint waypoint, since I want to remember the exact joint values, but this isn't always the case, as we'll see shortly. Very important, just like with the pallets, we want to tag this point so the Jacobi Palletizer knows it's a point of interest. So we give it a home tag, press Enter, and now we're set. We want to then create a pick point. the pick point needs to be on the corner of the conveyor or whatever delivery system you have for your boxes for palletizing, a constant corner that can be used as a reference regardless of box size. For example, all of our boxes are aligned and end up at this corner, so we'd set this as our pick point. Here, I'd use a Cartesian coordinate, because we care more about getting to this point than we do about exact joint values. After all, we could get any different size of box showing up here, and we don't want to make joint values fixed, or it can't adapt to that. But we also do want to prevent spurious inverse kinematics, like situations where the robot tries to reach this position from upside down. To prevent this, we just set a reference configuration by clicking this check mark here. It remembers the current joints of the robot, and during motion planning, we'll pick a joint configuration as close to this as it can. So that way, it'll be reasonable when palletizing. This is very important that you set your pick point this way. You also want a tag, just like with home, calling this point pick. Now that we have multiple waypoints, and let's disable collisions for a bit, we can jump between one and the other, make sure these make sense. We can either jump from right here where the waypoint is defined, or we can do it in the robot menu as well with the dropdown. See how where the robot ends up is based on the flange to TCP we set earlier. If we change it to be different, the robot will behave differently when it tries to reach this spot. So be very cautious of how you set that value. You can use the Motions tab to do some on-the-fly motion planning as well. See how the robot moves with our Jacobi software and plans motions between points. We can see the same as it's trying to go from home to pick. We can create a new motion for it. And we can see how it behaves. And then we can do the opposite. A question you might have is, hey, how do I actually make sure this point is reflective of reality? After all, I did a lot of measurements, and I want to make sure that the point I call the pick waypoint is actually reflective of what the corner of the conveyor is. To confirm this, we can go through a back and forth technique of probing the robot cell, making sure the coordinates are correct. It might help actually to create a new copy of this project to play around in. I'll create a duplicate just like this and work here. I'll rename it to, press enter, so I know why this is here. I can jog the robot in the real world and bring it to the desired points I want. I can then put those joints right into the system and confirm what the robot looks like it should at that point. Of course, if you're doing calibration and probing, you probably don't want to have the actual gripper on. You might want to install something like this on your flange, and then reflect that in the robot by setting the flange to TCP accordingly. Then you can move around in space and corroborate the readings your robot gives you for its joint values with how it looks in your cell. This back and forth iterative process lets you confirm that what you have for the cell is correct. Once you feel good about your project, we can go to the Settings tab to play around with a couple of features. We can share the project with other collaborators who can edit the project, but not delete it or share it themselves. If we want a fancier view of the robot cell, we can even flick on these two options to see how it looks. Studio Live is only a concern for simulation, but we have this to work with our Jacobi motion libraries, so you can test motions with our library and stream them to Studio to see how it performs. Once you're done with the project, make sure to save and export your project. It'll be saved to your system as a .jacobi_project file, and it is the file type we use in our Jacobi ecosystem. Thanks for watching, and I'll see you in the next video.